Hello, my name's Ross Clark, and in this video I'm going to present a brief overview of our ICML 2024 paper studying K-FAC heuristics by viewing Adam through a second-order lens, produced jointly with Miguel Hernandez Lobato. In our familiar machine learning training setting, we select model parameters theta to minimize some loss function f. For this work, we'll use the shorthand gt to indicate the gradient of f evaluated at the parameters at time t, and ct to indicate some curvature matrix evaluated at those parameters. The Hessian, Fisher, and Gauss-Newton matrices are all potential choices here, but we'll consider a general matrix for the moment. With this notation, we follow the convention that first-order optimizers compute parameter updates u using some function of the gradient information alone, whereas a second-order optimizer will additionally include information from the inverted curvature matrix somewhere in its update rule. This sets up a classic trade-off. First-order optimizers are generally cheaper to execute per iteration than second-order methods because they don't have to deal with an intractably large curvature matrix. But the second-order optimizer's more intricate model of the objective will give theoretically improved convergence properties, at least in the mathematically nice convex regime. Of course, neural network training is not a convex optimization task, so naive implementations of second-order optimizers generally give unstable results. However, our previous studies have found that K-FAC is a surprisingly strong competitor to many first-order methods. The K-FAC algorithm combines an efficient factorization of the Fisher curvature matrix with a variety of heuristics including smooth preconditioners, damped curvature, and adaptive hyperparameters. In fact, it seems that these kinds of heuristics are essential for second-order methods to perform well in practice. This leads us to ask whether the second-order optimizer's improved model, or their heuristics, are more responsible for their performance. In particular, we ask if we could take some of those heuristics, apply them to first-order methods, and observe a similar improvement in optimization performance. That idea is the focus of this work. We selected two heuristics from K-FAC to examine, both of which use an approximate model M, which is the Taylor expansion of the objective f about the most recent parameters theta t-1, truncated to second order. Having selected an update direction d, and assuming that c represents convex curvature, we can solve directly for the unique learning rate alpha, which minimizes the second-order model along this direction. Because this is now a one-dimensional problem, we can derive the solution in closed form. Moreover, the large curvature matrix only appears in products with the vector d, so we can exploit the Jacobian vector product trick to compute the solution without ever having to realize the full curvature matrix. Having chosen this learning rate, we apply the adaptive Levenberg-Marquardt damping mechanism as used by K-FAC. We compute a reduction ratio ρ, which compares the change in loss we observe from updating the parameters with the change in loss predicted by the quadratic model. Based on this ratio, we apply K-FAC's thresholds to decide whether to adapt the damping parameter lambda. Broadly speaking, a higher lambda causes the update to tend more towards a gradient-based rule, whereas a smaller lambda causes us to place more trust in the second-order model M. We refer to this entire strategy as a quadratic learning rate, or QLR heuristic. Motivated by similarities between the empirical Fisher matrix and the second moment gradient buffer V, we combine this heuristic with the Adam algorithm. On the left, we quote Adam from Kingma and Ba's original paper, which we simply follow as normal until an update direction D is chosen. At this point, we insert our heuristic, which computes a dynamic learning rate using an adaptive damping coefficient. By analogy with Adam and K-FAC, we use the Fisher information matrix as our curvature matrix in these expressions. We can then use our dynamic learning rate to compute the actual parameter update. This modification can be applied to Adam with minimal difficulty, and can similarly be applied to a range of other first-order methods. We can now use AdamQLR as a tool to empirically study Adam and K-FAC. We performed a broad range of experiments which are presented in more detail in our paper, but we'll briefly discuss two of our result sets here. First, we discovered that when AdamQLR is applied with some specific default hyperparameters which we propose, its performance is fairly robust. Here we see the effect of taking the adaptive learning rate selected by the QLR heuristic and multiplying it by some constant k to test for systematic bias in the choice of learning rate. In fact, the best optimization performance tends to be found when k is approximately 1, indicating our heuristic generally makes an effective choice of learning rate. When we directly compare AdamQLR to other algorithms, as in this experiment training a ResNet 18 on the SVHN dataset, we find the optimization performance is broadly comparable to other methods in use by the ML community. Specifically, the QLR heuristics are generally able to improve on Adam's performance, producing a loss trajectory which compares quite favourably with K-FAC in spite of the latter's more complicated underlying model. This suggests a naive second-order model is not the correct approach to training a neural network. In fact, the heuristics do seem to be playing a larger role in the performance of these optimizers than the second-order logic itself. In summary, we introduced the hybrid AdamQLR algorithm as a tool to examine the role of heuristics in K-FAC. We found that these heuristics have varying effects on different problems, with our results effectively performing a partial ablation study of K-FAC, suggesting that these heuristics are, in fact, a very important component of the optimizer. Tangentially, we find that an untuned version of AdamQLR is generally robust to its hyperparameters, so to some extent makes a compelling choice as a machine learning optimizer in its own right. As future work, we are interested firstly in understanding why the relative performance of the different optimizers changes so much amongst different datasets, in the hope that we can harness and control the underlying mechanism responsible. But more broadly, our particular combination of first and second order techniques is only one of a vast array of possible approaches we could have used. We think this provides a promising indication that useful insights could be derived from alternative formulations of the same idea. We look forward to seeing where this line of work leads as the field advances. Thank you for watching this paper overview. If you're interested in finding out more about this work, we encourage you to read our full paper or visit our poster at ICML 2024's Tuesday afternoon poster session, where we'll be at location 4-9 in Hall C.